Alright, welcome back. We're doing section B now. Again, just have a quick read through the instructions. Most importantly, if there are questions that have more than one mark, appropriate working must be shown. But most of the time you're going to be showing your working anyway, even if it is one mark, just because that's the nature of the questions. If a answer box, now this is a very common mistake, actually not that common, but people do make it. If an answer box has a unit printed in it, give your answer in that unit. Sometimes people, they're doing their working out and they end up with an answer, and it could be like, I don't know, 100,000 volts or something like that, which would be 100 kilovolts, right? But the answer box only has V for volts. I would not put a little k in front of the V in the box. I would just write 1 times 10 to the 5 or whatever it is volts, just to be sure. Okay, just to be sure. Alternatively, if the answer box has kilovolts, don't cross out the k or anything like that and write it in volts. Just leave it with the kV and do your conversion from volts to kilovolts, so divide by 1,000, right? So just keep that in mind when you're doing this. It's really the only other advice that I can give at this point. Alright, let's just make a start. So, question 1. Tugboats often have to tow other boats around the Port of Melbourne. Boat 1, a tugboat, over here, with a mass of 2.5 times 10 to the 5 kilograms, is towing 2 larger boats as shown in figure 1. All 3 boats are moving in a straight line, and boats 2 and 3 do not have their engines on. Boat 2 has a mass of 5 times 10 to the 5 kilograms, and boat 3 has a mass of 6 times 10 to the 5 kilograms. A resistance force of 1.2 times 10 to the 4 newtons acts on boat 2, and a resistance force of 1.4 times 10 to the 4 newtons acts on boat 3. The tension in rope 1 of here is 9.2 times 10 to the 4 newtons. There is a lot of information there, but everything's summarized neatly in the diagram in the figure, so we can just refer to things as we need to. Don't get too caught up in all the numbers, just wait for the question. Part A, show that the acceleration of the two boats being towed, boat 2 and 3, is 6 times 10 to the minus 2 meters per second squared. Alright, so this is only 1 mark, so it shouldn't take too long to actually figure out what we need to do here. We've got, basically, if you ignore boat 1, if you ignore the tugboat, just pretend that boat 2 is propelling itself forward with 9.2 times 10 to the 4 newtons of force. Okay, I know it says it isn't, but for all intents and purposes, we can pretend that it is. Alright, and we want to show that the acceleration of these 2 boats is 6 times 10 to the 2 meters per second, or 6 times 10 to the minus 2. Alright, so what we need to do is, if we're trying to work out acceleration, there's not really any other information that we could use in here other than using F equals ma, right? So the net force acting on boats 2 and 3 combined as a system will be equal to the mass of that system times the acceleration of that system, and that's what we're interested in finding. What is A? So if I do some rearranging, A equals the net force on the boat 2, boat 3 system, and that's divided by the total mass of boats 2 and 3. Okay, so what is the net force on the boat 2, 3 system? Well, we have this, what I would call a driving force for that system, which is this 9.2 times 10 to the 4 newtons. So there's that pulling everything to the right, to the left, 9.2 times 10 to the 4. But we've also got these 2 opposing forces, which are the friction forces, or the retarding forces, or the resistive forces, whatever you want to call them. 1.2 times 10 to the 4 and 1.4 times 10 to the 4, acting on each of the boats. We don't have to worry about this tension here, because I know it says that T is pointing to the right, but that's the tension on boat 3 from boat 2. There is an equal and opposite force, that is the tension on boat 2 due to boat 3 pulling back the other way. So that's sort of an internal force that we can ignore because it doesn't have an overall effect on the acceleration of our system. So we can ignore that T for now and just subtract these opposing resistive forces. 1.2 times 10 to the 4 minus 1.4 times 10 to the 4. Okay, that is all over the total mass of the boat 2 and 3 system, which is just 5 times 10 to the 5 plus 6 times 10 to the 5. So 5 times 10 to the 5 plus 6 times 10 to the 5. And you can just chuck all that on a calculator and we end up getting 0.06 meters per second squared, which is indeed 6 times 10 to the minus 2 meters per second squared. Okay, so long as you have, I guess, this line with the right numbers in, that's enough to show it is only 1 mark. Okay, so you're not required to do any amazing work here. It's just write down the net force and the mass and you're done. Okay, all right. Now I will pause here and just say, I know these videos can seem like they've run on for a long time, but you have to remember I'm doing a lot of talking and explaining as I go, so don't use the length of the videos as a guide to how long you should be spending on each question. The length of the videos is because I'm talking the whole time and I'm trying to explain things as I go along. You're not going to be doing that in the exam. Everything's going to be internalized in your brain, in your head. Everything's going to be done at a much quicker pace when you're in the exam, okay, than what it seems here. So don't get too bogged down on the length of time I'm spending on each question. Again, as a guide, per mark you should be spending about a minute, maybe a little bit more than a minute for those questions, okay? Alright, part B. Calculate the tension T in rope 2, show your working. So going back to the picture, we're just going to sort of focus on boat 3 now, okay, and look at the forces that are acting on boat 3. So on boat 3 you have the tension sort of pulling it along. That's what's driving the boat to accelerate to the left. You still have that opposing resistive force, but there's no other forces involved here. Okay, there are just the tension pulling it along, causing it to accelerate, and the opposing force. Okay, so if you just focus on boat 3, so focus on boat 3, we have that the net force, and just remember, net force, you can write it as mass times acceleration, but you can also write it as literally the sum of the forces acting on that object. So in this case, that's what we're going to do. We've got tension pulling it along. Now I'm saying the left direction is the positive direction because that's the direction that our boats are accelerating in. So tension will be a positive force, and we have to subtract opposing forces, which is that resistive force of 1.4 times 10 to the 4. And we know net force is equal to mass times acceleration. The mass of boat 3, 6 times 10 to the 5 kilograms. And that is times the acceleration of boat 3, which we know from part A is 6 times 10 to the minus 2 meters per second squared. Okay, and then solving for T, we end up getting, I'll just write it all out, but 6 times 10 to the 5 times 6 times 10 to the minus 2 plus 1.4 times 10 to the 4, and shoving that on a calculator, we end up getting 50,000 newtons, or 5 times 10 to the 4 newtons. Okay, significant figures. Let's talk about that quickly. So, I mean, the least amount of significant figures in any of our data in this question is 2. So they're all given as 2 significant figures in every number that you see here. So your answer should be 2 significant figures. Don't get too bogged down on it. The assessors don't mind that much. What they're really interested in is your understanding of the physics and Have you shown appropriately your understanding through appropriate calculations or diagrams or explanations or things like that? Okay, physics cares a lot less about significant figures than, say, chemistry, but don't overdo it, right? Don't round too much. And also don't round in the middle of a question if you're going to use that number later on for another calculation. Try and keep sort of everything as unrounded as possible. Okay, so that's question 1. Question 2. Engineers are testing a new high-speed electric vehicle on a high-speed test track. In one test, the electric vehicle travels around a circular banked track with a radius of 1.2 kilometers. The angle of bank is 33 degrees. This is shown in figure 2. Cool. So we have a banked track. The car looks like it's coming out of the page at that point, but imagine it's just going in like a circular path around like that, which has a, well, that's not the circular path. The circular path would be more like that, going out of there and coming back in like that, and has a radius of 1.2 kilometers, 1,200 meters. All right. And question A says calculate the maximum speed the car can travel around this banked track if there is no sideways friction between the wheels and the track. Show your working. Now, I am of the school of thought that you should put more working out than you think you need, but don't put working out that is useless and unnecessary. So there is a simple formula that you can derive, and you probably have done this in class, where you get a formula that is V equals root G times R times tan theta, where theta is the angle of the banked track and R is the radius of that that circular track that you're going around. V would give that maximum speed that is attainable without relying on friction, sideways friction between your tires and the road. Okay. According to the examiner's report, this equation and inputting the correct values in was enough, was satisfactory to answer this question. And if I do that quickly, we end up getting so 9.81. Again, being careful with the new value for G. It's not 9.8 anymore, it's 9.81. Radius of the track is 1.2 kilometers or 1,200 meters. And tan of 33 degrees is what we're putting there. And we're going to be ending up with roughly 87 meters per second as our maximum speed. Okay. Now, for 3 marks, I mean, I wasn't an assessor this time around, so I can't tell you exactly where these 3 marks might have come from, but possibly a mark for identifying that this is the correct equation that is required, a mark for inputting the correct values in, and then a mark for the right answer, but that seems a bit wishy-washy to me. I'm just going to go ahead and show you where this comes from. So, I mean, if you like, skip ahead to the next part of the video, the next question. I would probably try and derive this myself in the exam. I know it's going to take a lot of time. Worst case scenario, go ahead and just put that in, and you should hopefully get the full marks for future exams. But I'm going to quickly show you where this comes from if you're stuck and you can't figure out what to do for a question like this, or you just don't have that equation on your formula sheet, something like that. Okay. So looking at the car, we have some forces acting on it. There is gravity, mg, and there's a normal force acting on the car as a whole, which is perpendicular to the surface that it's on. Whoops. Which I'll just call N. And there is no sideways friction on the car, okay? So there's nothing pushing the car down or up this slope. Alright, so those are the only 2 forces that are involved. Now, because the car is traveling horizontally, okay, it maintains the same height from the ground at all times. So that means the center of the path of this car is directly across from it, okay? So it's in line with the center of its circular path, which must mean that there is some centripetal force pushing the car directly to the right at that point in time, okay, directly to the center of its circular path. That force comes from the unbalanced normal force, okay. Now it's not, the car isn't moving up or down, okay, it's maintaining the same height, which means the vertical forces must cancel out, all right, which means that this vertical component of the normal force must be equal to mg, okay. Now this little angle in here, that is my banked track angle. If you can't see that, just try your best. All right, and this little part here, that is the horizontal component of the normal force, which we said is what's providing the centripetal force causing the car to go in a circular path. Okay, so how do all these quantities relate to one another? Well, using this right angle triangle that I've developed up in the top here, we can see that the vertical component of the normal force would be equivalent to the normal force times cos 33. And we know that because there's no vertical motion of this car, it maintains a constant height, that must be equal to the gravitational force, okay? And then what we can derive from this is that the normal force is equal to mg over cos 33 degrees. All right, let's leave that for a second. Now, the horizontal component of our normal force, this can be written as n sine 33 degrees, and we know that that is providing the centripetal force in this scenario. Now, centripetal force, when we're dealing with an object in circular motion, we can write it as m times v squared on r, okay? But we know what n is. We know that n has a value of mg over cos 33, so I can go ahead and replace that with mg over cos 33, and the sine 33 is going to live in the numerator with the mg. Okay, and that's over cos 33. And hopefully you guys have been taught, whether or not you do methods or not, but sine over cos is equal to tan. So this ends up being mg tan 33 degrees. Okay, and hopefully now you can start to see where this formula comes from. So now notice that there's an m on both sides, so I can get rid of that, and I can bring the r over and then root the whole thing, and so I end up getting v equals square root of g times r times tan 33 degrees. Okay, and if you sub in your g and your r, then we go back to where we started here and we get the 87 meters per second. Okay, now again, this level of showing you're working out, I mean, it's probably overkill. So, you know, if you're strapped for time, just go ahead and plug in the appropriate formula. You should have this on your formula sheet. If you don't, make sure it's on there. And at the very least, make sure you know where this comes from and how you could derive it yourself if you're in a pinch. Okay? Because that's the real understanding of physics. Not just looking at an equation and say, okay, that's the one I use. It's saying, I know where this equation comes from. I could derive it myself if I needed to. All right? So there you go. It's 87 meters per second. Chuck it in here. All right, question 2b. Explain how the normal force from the banked track provides the centripetal force on the car. And like I said before when we were deriving this equation, is that the centripetal force is provided by an unbalanced horizontal component of that normal force. Okay, so what I would write is something like this. A component of the normal force acts as an unbalanced force pointing to the center of the car car's turning path. Okay, and that should tell the examiner you know what you're talking about, because like I said, in order to derive this equation, we have to understand that it's this component of the normal force that is providing that centripetal force, causing it to turn, basically. Alright, that's it for question 2. Question 3. This seems to be a projectile motion question. A golf ball near the edge of a cliff is hit at a speed of 48 meters per second and at an angle of 35 degrees to the horizontal, as shown in figure 3. The golf ball lands on the ground 6.2 seconds after it is hit. Ignore air resistance. Cool, so we're up here on the cliff, hit the ball, and it goes over there. Determine the height h of the cliff. Okay, so whenever we are dealing with what seems to be a projectile motion question, we like to write down as many things as we know about this situation. So we know that it's got some starting velocity, and that starting velocity has both horizontal and perpendicular components. So I'm going to write down those horizontal and perpendicular components. Whether or not we need them all for this part of the question doesn't matter. Ux is the horizontal component, and you can see from the right angle triangle that we have here, alright, Ux is cos of 35 times the 48. So 48 cos 35 degrees. And similarly, we can look at the vertical component, which is the sine of that triangle, which is 48 sine 35 degrees. All right, I'm going to leave it like that. I'm not going to calculate what those are just yet. All right. Now, what do we know about this situation? Well, the height of the cliff. Okay, well, the height of the cliff is basically can be thought of as the vertical distance that the ball travels in this time span. Okay, because if you're starting here and then at the end, doesn't matter how your ball traveled. Okay, you start here, but you end here. Okay, you end at that vertical height. We want to know basically what the vertical displacement is in this situation. So we want to know Sy. Okay, that is our unknown. We know about the situation, the vertical velocity, or at least the initial vertical velocity. We also know information about the vertical acceleration, which is the acceleration due to gravity. I'm going to say up is the positive direction, down is the negative direction. So acceleration is negative 9.81, and we also know the time span in which the ball performs this action. Okay, it hits the ground 6.2 seconds after it's hit by the club. So we know t is equal to 6.2 seconds. All right, so I want to work out vertical displacement. I know acceleration, I know time, I know initial velocity. You look for the appropriate Suvat equation to help you out here, and that equation is S equals ut plus half at squared. Okay, substituting everything we need into here, we don't have to do any transposing of this equation because we already want to work out Sy. So u is 48 sine 35 times t, which is 6.2, plus half times acceleration, which is negative 9.81, times t again, which is 6.2, and that's squared. And now you just chuck all that on a calculator and you end up getting minus 17.86 meters. And what that minus sign is telling us is that we've ended up 17.86 meters below where we started. That's all that's saying, okay? And therefore you can make a justification. Whether or not you want to write it out, you can just say therefore the cliff is, therefore h is equal to 17.86 meters. Okay. Significant figures, everything there is in two significant figures, so you could just say 18. meters if you like, and that should be sufficient. There we go. That's that one done. Alright, question 3b. Calculate the horizontal distance x that the golf ball travels before it reaches the ground below. Some of you may have an equation on your formula sheet that will give you the range of a projectile, but you might have only the specific equation that governs the situation in which the ball or the object lands at the same height from which it is launched. That's not what's going on in this situation. It lands at a different height from where it's launched, so you can't use that particular equation. We can do this very simply just using speed equals distance over time, right? So what are we trying to work out? We're trying to work out horizontal distance x, which is like horizontal displacement, sx. We know information about the horizontal speed, the initial horizontal speed, and because there's no air resistance, that doesn't change over time, so that's a constant value. And we know the time that the ball is in the air for, okay? So this is just straightforward speed, distance, time, right? Speed equals distance over time. We are trying to work out distance, so distance equals speed times time, right? So Sx is equal to Ux times t. Ux, we said above, was 48 cos 35. Again, notice I haven't actually worked out what that is. I've tried to keep it as unrounded as possible. And t was 6.2 seconds. And, oh my god, what is going on with that time symbol? Right, chuck that on and calculate it. You get 243.78 meters. Which, again, significant figures wise, we could just round it to 244. That should be fine. Okay, and that's it, we're done. Part C, describe how in real life air resistance would affect the golf ball's flight path. Okay, I'm going to highlight flight path here because that I think is very important in how the examiners want you to answer this question. Okay, flight path refers to both what's happening horizontally and vertically during its flight, right? Now, air resistance would have an effect on both the horizontal and vertical components of its velocity during the flight, won't it? Because air resistance wants to hinder the motion of that projectile, okay? So the resistive air resistance would, I guess what you could say is cause a deceleration in both the horizontal and vertical directions. And then that would, I guess, lead to a shorter, or a lower maximum height and a shorter horizontal distance. So however you want to write that out, I'll just spend some time doing that quickly. If you want to just skip ahead to the final part, that's fine. So I'll just say, it's going to be a bit of silence here while I just write things down. Alright, so again, I've said the resistive force would cause a deceleration in both the horizontal and vertical directions, leading to a decreased maximum height and a shorter horizontal range. So we're addressing both the horizontal and vertical parts of that ball's motion. Okay, if you just said it would have a shorter height, or if you just said it would have a shorter horizontal range, you'd probably only get 1 mark for that question. Okay, you'd have to address both directions there. Question 4. The safety of passenger cars can be assessed using simulated collisions with a crash test dummy in the passenger seat. For figure 4 shows a dummy without a seatbelt in a car traveling towards a fixed solid wall. Goodbye dummy. During an initial test, the dummy is seated in a car with no front airbags fitted. When the car hits the wall, the dummy experiences a force as it collides with the interior dashboard of the car. This force varies with time as shown on the graph in figure 5. So we have a graph here of when the dummy hits the dashboard, and there must be some sensor on the dashboard that tells you how much force is being applied to it over time, and it produces this graph here. Alrighty, part A. Determine the impulse on the dummy during this initial test. Alright, so looking at our graph, we have a force versus time graph. Just make a note, your time is in milliseconds, which is times 10 to the minus 3 seconds. Okay. When we have a force versus time graph, the area under the graph gives us the impulse on the object that this graph applies to. So that's all we're really going to be doing here. Determine the impulse on the dummy during this initial test. You can just say that the impulse equals the area, which if we go back, it's just a triangle, so half times the base times the height. The base is, what's that, 120 milliseconds it looks like. So let's write that out. Area equals half times, oh no, what am I saying? That's half of the base. The base is itself 240 milliseconds, but converting that into seconds, we get 0.24, and the height of our triangle is, what's that, 2,400? Ah, sorry, not 2,400, 24,000. Alright, and that gives us 2,880 Newton seconds. I'm just going to leave it like that. I'm not going to bother with significant figures here. Okay, you've understood what you need to do. They're not penalizing you on being too liberal with your significant figures. Alright, part B. In a second test, the dummy is seated in an identical car traveling at the same speed as the initial test, again without a seatbelt, but with front airbags fitted. The collision duration for the dummy in this second test as it collides with the airbag is double the time of the initial test without the airbags. The results of the initial test are shown as dashed lines on figure 6 below. Sketch on figure 6 how the force on the dummy could vary with time during this second test. Okay, so we know that the time has doubled for this collision. So instead of, where's my mouse? Instead of the collision lasting 240 milliseconds, it's now going to last 480 milliseconds, putting the end of the collision here. Now, it tells us that it's traveling at the same speed. Okay, so if it's traveling at the same speed, it has the same initial momentum, and if by the end it comes to rest, it has the same final momentum. Impulse is literally the same thing as the change in momentum. So if the change in momentum is the same for each scenario, the impulse must be the same for each scenario. Now, if we're doubling the time, we need to somehow ensure that the area of this new graph that I'm producing is the same as the area of the initial graph that was there. And the only way that can be done, that can be done, is if we halve the height. Okay, because if we look at the area of a triangle, half times base times height. If you double the base, which is what we're doing, half times 2b, then in order to have the same area, we need to halve the height. And then that 2 and that half will cancel out, and we end up with the same area that we had before. So the height of our new graph is going to be half of 24,000, which is 12,000, which is going to be here. And the midway point, I guess, would be here as well, because that's half of the time duration. So if I sketch a graph, I don't have a ruler right next to me, but you should have a ruler with you when you're doing these questions, and just draw another triangle that looks like that. Okay, and that triangle will have exactly the same area as the initial triangle. So 2 marks, I guess 1 mark for putting in the right time here, which is 480 milliseconds, and then the right height, which is 12,000. Again, that's just to ensure that the 2 triangles have the same area, which means they have the same impulse, which we know because the car is traveling at the same speed as it was in the first scenario. Alright, that's it for question 4. Question 5. A basketball of mass 0.63 kilograms traveling vertically down hits the floor at a speed of 12 meters per second and rebounds at a speed of 10 meters per second as shown in figure 7. Calculate the magnitude and direction of the change in momentum of the basketball. Okay, so what is change in momentum? Change in momentum is the final momentum minus the initial momentum. Let's give some signs here. So let's say down is negative and up is positive. So initially it's traveling at negative 12 meters per second, and then after the collision it's traveling at positive 10 meters per second. So the mass does not change in this question, assuming the mass is a constant 0.63 kilograms, so we can go ahead and just use that same mass for the final and initial momentums. By the way, if the mass doesn't change, then the change in momentum is mass times change in velocity, which is probably a bit easier for our calculation here. 0.63 times, okay, change in velocity, final velocity minus initial velocity. Final velocity is this positive 10, okay, minus the initial velocity, but the initial velocity itself is negative, so be very careful with your sign conventions when doing change in momentum questions. It's very easy to miss negative signs, and that'll make your answer funny. Okay, so we end up getting 0.63 times 10 plus 12, chuck all that on a calculator, and we end up with 13.86 kilogram meters per second, and we'll just go ahead and call that 14 because everything's in 2 sig figs. Alright, so we can fill that in. And what is the direction of the change in momentum? Well, look at our sign conventions. We've said that up is positive, down is negative. Our final change in momentum was a positive number, so that means the change in momentum must be up. So you can draw an arrow, or you can just write up. And that's your 2 marks, 1 for each box. Part B. Is the collision elastic or inelastic? Justify your answer. No calculations are required. So a collision is elastic if it has the same kinetic energy both before and after the collision. Okay, or if there are multiple objects involved, the total combined kinetic energy before the collision should be equal to the total kinetic energy combined after the collision. We're only considering the ball here. This is like an immovable floor, so we're just focusing on the ball here. Is the collision elastic or inelastic? Well, you can see that it has 2 different speeds before and after the collision. So obviously the kinetic energies before and after will be different because kinetic energy is dependent on speed. How you want to write that out and how you want to explain that, that's really up to you. I'll write out my own sort of interpretation of this. So first of all, is it elastic or inelastic? That's 1 mark. You say it is inelastic. And y. So I'll just write that out. Skip ahead if you want. Alright, so I should also mention with the same mass, because it is not unentirely impossible that for some reason the mass has changed before and after the collision, which means that just because of this equation the kinetic energies might turn out to be the same, but we're assuming that there is no mass changed in this collision. But basically, again, we say the collision is inelastic because the speeds before and after the collision differ, and since the kinetic energy is dependent on speed, the kinetic energies before and after the collision are different, with the mass staying the same. Okay, and that's the definition of an inelastic collision. It's when your kinetic energies are different before and after the collision. So that's that. Moving on. Question 6. Jenny and Kwan are discussing how the International Space Station ISS supply craft missions operate. The station is resupplied with food, water, air, fuel, scientific equipment, and other necessities every 3 months. Kwan suggests that the supply craft could initially be put into circular orbit relative to the ISS, as shown in Figure 8, before it eventually docks. So what he's saying is that there's the ISS. The ISS is, wherever it is in orbit around Earth or whatever. But they're sending a supply craft up to there, and that supply craft itself is going to be put into orbit around the ISS. So it's kind of like the ISS is the Earth, and the supply craft is like the Moon, right? The centripetal force needed to keep the supply craft in orbit, Kwan argues, is provided by the gravitational attraction between the supply craft and the ISS. Kwan calculates that an orbital radius of 500 meters could be achieved with the supply craft traveling at a speed of 0.436 meters per second. The mass of ISS is this, and the mass of the supply craft is this. Will Kwan's suggestion work? Justify your answer with appropriate calculation. So again, we need to unpack what's being asked of us here, okay? The question itself is, will Kwan's suggestion work? Well, what is Kwan's suggestion? So Kwan says that if they put the supply craft this distance, okay, 500 meters from the ISS, then the gravitational attraction or the gravitational force of the ISS on the supply craft is enough to keep it in this circular orbit at this particular speed. That's what Kwan is saying. He's saying that if I put my supply craft here, then purely just the gravity from ISS acting on the supply craft would be enough to keep it in this orbit at this speed. Okay? So in order to assess Kwan's suggestion, what we'd probably need to do is work out, if it was placed 500 meters from the ISS, what would be the gravitational force acting on your supply craft? Okay? And then from that, we could then say, okay, is that force enough force to keep it in this orbit with this particular speed? Okay, so there's going to be two parts to this question. So first part, we're going to see what is the gravitational attraction on that supply craft due to the ISS. Okay, so how can I put this? I'll just say force of gravity, or I'll say force of ISS on the supply craft. Okay, what is that? Well, it's just the gravitational force between two bodies, right? So it's going to be equal to G times m1 times m2 over r squared. G is 6.67 times 10 to the negative 11. M1 is the mass of ISS, let's say, so 4.5 times 10 to the 5. M2 is the mass of the supply craft, 1.5 times 10 to the 4, and that is over the distance squared, which is 500 meters squared. Okay, now if I put that on a calculator, we end up getting 1.8 times 10 to the negative 6 newtons. Okay, so what that's telling me is that if I put the supply craft here, ignoring everything else in the universe, okay, if it was just the ISS and the supply craft, the ISS would be exerting a gravitational force on the supply craft of strength 1.8 times 10 to the minus 6 newtons. Now, it's not a very big number, but who knows, could be enough to provide this particular centripetal force that's going to keep it at this speed. Okay. So now, ignoring this number, let's just say, okay, I want my supply craft to be traveling with an orbital speed of 0.436 meters per second, but at a distance with a radius of 500 meters. Okay, so what is the centripetal force that we need to do that? Okay, so I'll say centripetal force required for this particular setup of variables. Well, we know the centripetal force is equal to m. We've been given an orbital speed v and an orbital radius r. The mass of your supply craft is 1.5 times 10 to the 4. The orbital speed is that 0.436 squared over the distance r of 500. Okay, typing this into a calculator ends up giving you about 5.7 newtons. Okay, so what this is telling us is that we need this much force acting on the supply craft in order for it to achieve this particular orbit with this radius and this velocity. Okay, the only force available for us in this scenario is the gravitational force of the ISS on the supply craft. There's no other forces involved here, unless of course the supply craft itself has like thrusters or something that can help, but it doesn't say that. It just says, Quan says that this centripetal force is provided by the gravitational attraction, but it can't be, because the maximum force that could be given to that supply craft is 1.8 times 10 to the minus 6. However, we need 5.7 newtons of force in order to achieve this particular orbit. So Quan is wrong. Quan's suggestion will not work. Okay, so we can just then state that finally as something like the gravitational force alone will not be enough to provide the 5.7 newtons of centripetal force required, and then just say will Quan's suggestion work? So therefore, Quan's suggestion will not work. Okay, there you go. All right, so we've justified our answer with appropriate calculations, and we've also said will the suggestion work. All right, so that's your 3 marks there. All right, moving on. Question 7. An electron is accelerated from rest through an electric field, so that's going from here to here, I guess. It enters an area of constant magnetic field B of magnitude 5 millitesla over here, which is perpendicular to the electron's path. Once within the magnetic field, the electron follows a circular path of radius 1.5 centimeters, as shown in figure 9. You may ignore relativistic effects. Part A. Show that the electron's speed v as it enters the magnetic field is this, and it's only 1 mark. So there should be enough information here to just plug everything into a formula and pop out with a number, and that is indeed what we are doing. Okay, there is a formula governing the orbital radius of a charge that is moving perpendicular to a magnetic field. If it's moving with a particular speed and it has a particular mass and all that kind of stuff. So the formula is, it should be on your formula sheet somewhere. I think it's also on the data sheet that's given to you. R equals mv over qb. Again, R is the orbital rate, not orbital radius, the radius of the circular path that the charge will take. M is the mass of that particle with that charge. V is the velocity of that charge. Q is the charge of the charge, and B is the magnetic field strength. All right, we've got all that information here. Okay, R is 1.5 centimeters, B is that. It says it's an electron, so we know the mass and the charge because that's given to us in the data sheet, and we are required to show that V will turn out to be this if we plug everything into here. So rearrange. V equals RQB over M. R is 1.5 centimeters. Everything's going to be SI, just remember. So convert everything to meters, Tesla, kilograms, whatever. So R is 0.015 meters. That's 1.5 centimeters. Q is the charge on an electron. 9.1. Sorry, that's the mass. Silly me. 1.6 times 10 to the negative 19 coulombs, and B is the magnetic field strength, 5 millitesla, so we're going to just convert that to Tesla. Be careful. 5 times 10 to the minus 3 for milli, and then over the mass of the electron, 9.11 times 10 to the negative 31 kilograms. And putting all that on a calculator, you should end up with 1.32 times 10 to the 7 as shown. And that's it. That's 1 mark. Okay, literally just for getting the formula, rearranging it, putting the right numbers in. Part B. Calculate the accelerating voltage V0 needed for the electron to reach a speed of that. Okay, so what's going to happen here? We're saying there's a source for electrons. Okay, the electrons sort of meander into this electric field, and we can just basically say they start from rest, and they're being accelerated across. How are they being accelerated across? They are, well, there's some kind of accelerating voltage. Okay, and by the end of this journey, when they go from this opening here to this opening here, they will have gained speed, therefore they will have gained some kinetic energy. Okay, and the question is, well, is there a way for us to work out how much energy is gained given a voltage? And the answer is yes. Okay, there is a simple equation telling us that the work done on a charge Q by a voltage V is just Q times V. Okay, so the work done on this charge, on this electron, is Q times V0, but we also know that at the end of that sort of accelerating period, that electron now has kinetic energy equal to half mv squared. Okay, we know m, we know v, we know q, we want v0, so v0 is equal to, I'll put everything in one fraction, so we're going to have mv squared over 2q. M is the mass of the electron, V is its speed, which is 1.32 times 10 to the 7, and that's squared, and then that's all over 2 times the charge of the electron. Whoa. Okay, chuck all that on a calculator, you end up with 496 volts, roughly. Significant figures, I mean, there's 3 here, there's 3 here, there's 3 here, there's 3 here. So we'll just leave it as 496. Okay, I wouldn't round up to 500 there. Okay, so key takeaway from that question, anytime you're accelerating a charge with a voltage, the work done, the energy imparted, or the energy taken away from if you're decelerating it, is equal to Q times that voltage. Okay, and we set up a little equation for ourselves because we know that it has speed at the end, and that is its kinetic energy that it's gained. Part C. The electron is replaced by a proton traveling at the same speed. A proton has a mass of 1.67 times 10 to the minus 27 kilograms and a charge of blah, blah, blah. Describe the path the proton takes after entering the constant magnetic field compared to the path taken by the electron. Justify your answers. No calculations are required. 3 marks. Alright. Okay, so we're changing from an electron to a proton. Okay? So first thing you should realize is you're going from a negative charge to a positive charge. Okay? Now, go think of what's happening to the electron in this field here. Why is it going in this sort of clockwise path? That is due to the magnetic force, and you can use your slap rule to determine the direction of that force throughout this journey. So if you imagine the electron's just here, we're thinking about an electron at the moment, okay? So with electrons, I just like to use my left hand because they're negatively charged. You might have another way of doing this, but for me, negative charges use left hand, positive charges use right hand. So you're dealing with an electron, stick your left hand in front of you. Your fingers are the field lines. They are going into the page, as indicated by the crosses. So stick your left hand in front of you, fingers pointing away from you. Your thumb is the direction of the motion of the electron, so it should be pointing to the right. And if you're doing this with me, your palm should be pointing down. So the force on the electron at this point is down. Okay, that's going to cause it to curve. Then at the next instant, okay, the velocity is that way. So turn your hand a little bit. Okay, 45 degrees down. Your palm should now be pointing in that direction. It's going to cause the electron to curve even more. And that's what's causing it to go in a circle, sort of that constant force that's always pointing perpendicular to its motion, right? Now, if we change that to a proton with a positive charge, you now use your right hand. And so everything's the same, except your hand's going to be oriented differently because you're using a different hand, right? So your fingers still point away from you, your thumb's still pointing to the right, but if you're using your right hand, the palm is pointing up. So the force on that proton will be up, which means it's going to curve that way. Okay? So you can definitely say that the path will be anti-clockwise. Okay, so the path is now anti-clockwise since the magnetic force is reversed due to the positive charge compared to the negative charge. Okay, so that's one thing that will happen. What's also going to happen is the proton has a different mass to the electron. Okay, so the proton's got a much larger mass, times 10 to the minus 27 compared to times 10 to the minus 31. And because of this equation here, we see that if there's a larger mass, there's going to be a larger radius. So you can just say the radius of the path is larger due to the larger mass and also the fact that the radius is proportional to the mass. Okay, and that's all that you really need to say. That's it. How are we going for time? 1 hour. I might do one more question and then break it up into the next part. So question 8, we've got, okay, let's just do this. So electrical activity in thunderstorms can be modeled as charge separation, causing an electric field to form between the base of the thundercloud and the ground, similar to two charged parallel plates. Figure 10 shows the base of a thundercloud that is 850 meters above the ground. Alright, cool. Part A, using arrows, sketch on figure 10 above at least 5 electric field lines between the ground and the base of the thundercloud. Alright, so we're treating these as parallel plates. Alright, and hopefully in your theory you've just seen what the electric field looks like between them. If these were infinitely long, then you could draw straight field lines everywhere, but I'm going to be a little bit pedantic here and say in the middle, yeah, it goes up pretty much, maybe slightly to the side it goes up pretty much, but then as you get closer to the edges they sort of curve a little bit like that. Okay, and you're just being careful with the directions of the arrows. The electric field always goes out of positive charges and into negative charges. Okay, 5 field lines, there you go, that should be enough to convince the examiners you know what you're talking about. Part B, the potential difference between the ground and the base of the thundercloud is 1.2 gigavolts. Calculate the magnitude of the electric field between the ground and the base of the thundercloud. Okay, if you don't know what to do here, it's always sometimes handy to look at the units of your box that you've been given. So calculate the magnitude of the electric field. The electric field here is given to us as volts per meter. So maybe, if you don't know what to do, go looking for an equation that has something to do with electric field, voltage, and distance, right? And in this case, there's a simple equation for electric field, voltage divided by distance, okay? In this case, the voltage is 1.2 gigavolts, 1.2 times 10 to the 9, that's your giga. The distance between the plates, quote unquote, is 850 meters. And calculate a time, you get, where am I, 1.41 times 10 to the 6. Okay, significant figures, there's 3 here, there's 3 here. We're going to leave it as 1.41 times 10 to the 6. There you go. Part C. A 1.2 gigavolt lightning bolt discharges to Earth from the thundercloud with a current of 30 kiloamps for a duration of 60 microseconds. Calculate the total energy transferred by this lightning bolt. Give your answer to 3 significant figures. Highlight that because we want it to 3 significant figures. Okay, so what have we been given here? We've been given voltage, current, and time. Okay, they want us to get energy. Okay, what is the energy? Now there are a number of various ways to put these things together in order to produce energy throughout a calculation. The way that I saw this and initially thought about it was, okay, I know that energy is equal to power times time. In this case, we've got electrical power, and electrical power is equal to voltage times current. So the energy is voltage times current times time. Okay. That's just how I saw it initially. You might already just have this equation, energy equals VIT. That's fine. Nothing wrong with that. that's just the way I saw it. Okay. So if you chuck all your variables into here, 1.2 times 10 to the 9, that's your giga, times the current, 30 kiloamps, 30 times 10 to the 3, that's your kilo, and 60 microseconds, so 60 times 10 to the minus 6, that's your micro, and calculator time, you end up getting 2.16 times 10 to the 9 joules. Okay, and that's 3 significant figures as they require. Alright, good place to stop. I'll come back with the next part and then we'll keep going.